Hello and welcome back to MEC 416/816 Engineering Acoustics. In this lecture, we're going to finish and wrap up our discussion of single degree freedom oscillators, and specifically we're going to talk about power relations. So in this case, we're considering a harmonic oscillator with an applied external harmonic force. The equation of motion is listed as shown below, and then you could include some initial conditions if we wanted to. So in this case, the instantaneous power in watts that is supplied to the oscillator is given by, we're going to use capital pi here, capital pi sub I, and that sub I stands for instantaneous. It's a function of time. This is equal to f of t times x dot of t. So if you recall, when we looked at the work done by a force, we ended up with the integral over time of the force times the velocity. And so what's inside of that integral is the power, instantaneous power. Okay, so for a harmonic force, we are going to be most concerned with the power that's applied at steady state. We're not so much interested in the transient results. Again, we're interested in what happens in steady state. And so, quite simply, the power at steady state, instantaneous power at steady state, pi sub ss of t, this is going to be equal to that force times the steady state velocity x dot sub ss of t. So given our steady state solution, which was x ss of t is equal to big X times the sine of omega t minus some phase, we can then compute that steady state velocity x dot ss. Since the steady state amplitude is independent of time, we're going to just take the derivative of the sine term. We'll get x omega times the cosine of omega t minus theta. And again, theta does not depend on time either. And so therefore, the steady state power is going to be equal to, we're going to bring in that cosine, so we have f times the cosine of omega t times big X omega times the cosine. In fact, let's rewrite this. So we'll have big F times big X times omega times the cosine of omega t times the cosine of omega t minus theta. And that is our steady state power. And it tells us what it is as a function of time. However, because the power is oscillating due to that oscillatory force, we're going to be in most situations interested in the average power, which we'll just call big pi. And we're interested in what is the average power being applied or supplied to that oscillator. And often this is going to be more significant than that instantaneous steady state power. So we're going to compute the average power as follows. First, the average power big pi is going to be equal to, we're going to end up doing an average of this using integrals. We're going to take 1 over a single cycle duration, big T, and that's the period of the applied forcing, big T. This times the integral from 0 to t, big T again, of cosine. And in fact, at this point, let's just leave it as big pi ss dt. This is the definition of a temporal average. And we can also write this as using square brackets of pi. And that should be pi ss. Let me erase here so I can rewrite this. So we're looking at taking the temporal average. And we're going to write that. This is the temporal average. Where T, big T here is the duration of a single complete cycle of vibration. All right, so from here, we're going to substitute in, and it says 54 and 55 here. We're actually going to substitute 74 into 75. And doing so, we're going to end up with the following. The big pi is equal to the quantity f big X omega divided by big T times the integral from 0 to big T of the term cosine omega t times the cosine of omega t minus theta dt. t. We're going to split up this cosine term in the integral, and we'll find that big pi is actually equal to big F, big X times omega divided by big T times integral from 0 to big T of the quantity cosine squared omega t times the cosine of theta plus cosine of omega t cosine omega t times the sine of omega t times the sine of theta. All of that times dt. And this is an integral that can actually be solved. Let me rewrite that. So the sine of theta, big parenthesis here, dt. This is an integral that can actually be solved analytically. And when you do so, what you end up finding is that big pi is equal to big F times big X times omega divided by 2 times the cosine of theta. Let me redraw that square. There we go. Okay, so we know what X is, and we also know what theta is. So if we pull X from our section on steady state vibrations, for cosine of theta, this is actually going to be equal to b divided by the square root of b squared plus the quantity k over omega minus m omega, that quantity squared. We substitute these in. What we'll end up finding is that the average power, big pi, is equal to big F squared times b divided by the quantity. In fact, let's do the denominator first. So we're going to have b squared plus k divided by omega minus m omega, this quantity squared. And then in the numerator, we have F, big F squared times b. Or what this ends up being is that big pi, or the average power in steady state, is equal to the applied forcing amplitude squared times the damping coefficient b divided by the mechanical resonance squared, or mechanical impedance squared. So again, if we know the mechanical impedance at any frequency, then we can determine what the average power will be supplied by a harmonic force at that frequency. This concludes our discussion of single degree of freedom oscillators, and in the next chapter we're going to cover the oscillations of strings, bars, and other one-dimensional wave equation systems.